Hello, Math 8 students. This is Open Up Resources, Unit 1, Lesson 7, No Bending or Stretching. Our warm-up today to get started is measuring these line segments. You can see this line segment here right below this ruler, and the directions are find the length of the segment to the nearest 1/8 of a unit. Talk me through the strategy that you used, looking for lots of hands right now. Waiting for some more hands. In-person students, you are helping our online learners. Thank you. Angel, how did you do this? Okay, and so I think that it's pretty easy to see that this line goes to here, right? Like we can see right up above it is this tick mark. The question is though, how do I state that measurement to the nearest 1/8 of a unit? Looking for some more hands to add to what Angel said. Parker, please share your strategy.
All right, so how you can tell if the little lines on it are measured by 8?
How do you know that they're measured by 8? You can count them, and there's 8 of them. I'm going to fine-tune that a little bit. Pick a one unit marking, because there's more than 8 for sure. However, within 1 to 2, that's where I'm counting 1, 2, 3, 4, 5, 6, 7, 8. So that means each one of these is 1/8. Who did it a different way? Okay, you need a different strategy for the future, so please pay attention to this different strategy. Between a set here, a unit, I can see that this tallest mark splits it in half. And then the next tallest mark takes those halves and it splits them in half, making each one of these markings a fourth. And then we can see that within the fourth, we have another marking splitting it in half, making each one of those an 1/8, confirming and showing in a different way that we know that each one of these tick marks is an 1/8. So when I am asking for this to be measured to the nearest 1/8 of a unit, we can see that it's between 4 and 5. So do I just say 4? Do I say 5? How do I measure to the nearest 1/8 of a unit? Okay, that's fine. I'll just stop the recording and I will just... Hello, Math 8 students. This is Unit 1, Lesson 7 from Open Up Resources, No Bending or Stretching. Your warm-up today is to measure each one of these line segments following the specific directions for that problem. The length of this segment needs to be measured to the nearest 1/8 of a unit. So what I'm noticing is that between any particular unit, any piece from the 0 to 1, the 1 to 2, I am seeing that there are 1, 2, 3, 4, 5, 6, 7, 8 segments, making each one of those little tick marks 1/8 of a unit. But because I know what the future problem is, I'm also going to be looking at this, seeing that this right here splits the 2 and 3 in half, this right here. So I know that this is the half unit mark. And I can take that half unit mark and I can see that this line right here splits this half into half again, making this 1/4. And I can see that it's split yet again to 1/8. And that's going to be really helpful as we have to define our own tick marks on number 3. So measuring this actual line segment, we can see that it is between 4 and 5. How far along is it? Again, these are our 8 units. 1, 2, 3, 4, right there takes me to 4 and 5/8 of a unit. You'll notice that on number 2, it is a little bit of a different scale. We don't have eighths anymore, which is great because the directions say to the nearest 0.1 of a unit. So that's our clue right here, this 0.1 of a unit, that we're using a different measurement system. And 0.1 of a unit, when we actually say this number the right way, it's 0 and 1/10, 1 in the 10th place, which tells us exactly how it's going to look as a fraction, 1/10. So if we kind of count like we did before, we can see that between this 0 and this 1, there are indeed 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That makes sense that these are 1/10 tick marks because there are 10 of them there. You can also observe similarly that if we pick any other place, we see this big long line in the middle. That's because that's breaking it up into half. But all of the other tick marks are all the same, meaning that they're all split up. So I would then continue to count and see, oh, it's splitting this into fifths and this into fifths, so all together into tenths. So as I measured this line segment, I can see that it is longer than 4, not quite as long as 5, and I could count 1, 2, 3, 4, 5. But knowing that this is half, and that's already going to be 5/10, I can just jump up to 6 and 7/10 and get 4 and 7/10. And all of that is incredibly helpful because for this third measurement, we can see we're answering two questions. First, it says to the nearest 1/8 of a unit, and then it says to the nearest 10th of a unit. So I actually need to do two little measurement systems here. That first one, to the 1/8, means I need to split this up into half first. And once it's split in half, then I can split it into fourths, and then I can split it into eighths. And now that I've done that, I can actually go back and count and say, okay, it's more than 3, not quite as much as 4. 1, 2, 3, 4, 5, looks like that is 6/8. So 3 and 6/8 of a unit. And even though it says to the nearest 8th, I don't like having unsimplified fractions, so I will also say 3 and 3/4 of a unit. Probably a precision here to make sure that we are using units on each one of these as well. We're not just going to be lazy and say 4 and 7/10 or 4 and 5/8 like I initially tried to get away with. Please include the units. Now, as we switch gears and look at problem 4, now we need to take those same measurements, the same length, and now we need to use tenths. So that means I'll still need to find that half, but now I'm splitting it into tenths. So half, 5 on one side, 5 on the other side. I still can't get that quite in the middle. And so I would have 1, 2, 3, 4, 5. Those would be my tenth marks. And again, it's more than 3. There's the half, so that's 5, 6. Looks like it's about 7-ish, maybe. 3 and 7/10. Now, if you want to kind of check your precision on each one of these, 3 and 3/4 is 3 and 75/100, 3.75. And 3 and 7/10 is 3.7. So although these are different, and they should be because we're using different measurement systems, notice that those two estimates are still pretty close. 3.7 units and 3 and 75/100 are still very close together. As we move on to our next activity, we are going to be looking at certain features in all of the transformations that we have discussed so far. And we start by performing different transformations on different figures. And as we do that, we want to make sure that we are paying attention to specific characteristics. To get us started here, it says translate polygon A so that point P goes to point Q. So I am going to be moving point P to point Q, which means I am moving to the right. I'm going to fix that so that it actually shows a vector instead of just a line segment. Nope, that didn't work out. Let me try that again. Because translations are defined by vectors. Vectors show both magnitude and direction. And so this vector means that this point P is going to move that amount to Q, but that also means this point is going to move that same amount, and this point is going to move that amount, and this point is going to move that amount, and so on. And so it's really important to define that using the vector. I want you to make sure you write this in your notes. that when we translate, we need to make sure that we describe it with direction and magnitude, or in other words, a vector. Pencils are moving. Online learners at home, you guys do have access to some applets to complete these. And so you guys remember for sure that we need those vectors, because that's that first step in getting that translation to happen, is creating that vector. So just making sure we describe using the direction and magnitude, or in other words, that vector. As we perform this translation, this is going to be the new position. Again, you online learners have your applet and you don't need to struggle with this silly technology like I do. You can just simply move it. But here's what you need to do once it is moved into position. It says, in the image, write the length of each side in grid units next to the side. For example, I can see that this line segment right here is 1, 2 grid units. So I'm labeling it 2. I do want to compare, even though the directions don't say, I do want to compare it to the original, that pre-image. And that, you'll notice, is also 1, 2 grid units. Continue doing that for each one of those line segments. 1, 1. Interestingly enough, that's 1 and 1 over here as well. 4. Not too surprised to see that that side length is also 4. 2 and 2. 3 and 3. 1 and 1, and 2 and 2. Now I know that this seems obvious, but it is leading to a very important conclusion, and so I want us to observe and point out that the side lengths in the image and in the original, that pre-image, are the same. And we're writing that down because it's a very important conclusion. The side lengths in the image and pre-image are the same. And now we're ready for our next transformation, which is a rotation. Now this one, for students who are in person, you're definitely going to want to use your tracing paper. For students who are online, you do get the advantage of having the applet to help you with this. The first thing that I would like to point out, whether you're using the applet or using tracing paper, is identifying 90 degrees. Typically, when we see this isometric grid, we're rotating in 60-degree increments, because each one of these angles, you'll remember from our previous lesson, is 60 degrees. But it's not asking us to rotate 60 degrees, it's asking us to rotate 90 degrees. Which is still possible, but it does present a few challenges, so make sure you're paying attention. Knowing that this angle is 60 degrees, but the full angle in that triangle is 90 degrees, we can come to a conclusion about this amount right here. And that amount right there is 30 degrees. So again, remembering that the angles in each one of these triangles is 60, and this green piece that's already colored in, which is 30, it's easy to now conclude that this remaining piece that I'm going to color in purple is also going to be 30 degrees, because the 30 degrees plus this 30 degrees add up to that 60 degrees. And again, we can remember that all of these angles are 60, so if I have 60 degrees plus that purple piece, which is 30 degrees, we can then see what it is going to be like to rotate that 90 degrees. That means that this piece of the triangle is going to rotate 90 degrees. There was 30, and here's 60 more, and it is now going to lie somewhere on this line. As you are performing that rotation, please keep in mind what that 90 degrees is going to look like. Here's 30. Continue rotating that extra 60 until we make the full 90-degree rotation. When you rotate that triangle, this side needs to be right there. Make that happen, in-person students. Online students, let's take a look at your applet. And we can see that we are going to rotate, so I'm selecting this figure, this point, and making sure to type in 90 degrees clockwise, and it will take it to this position. The challenge that we have is that although this triangle had these nice, easy points to find, because it's where all of those triangles meet, all of the triangles meet here, when we rotate it, it no longer has that nice defined point. So it's a little bit harder to measure lengths, which is why the next thing that I need you to do, once that triangle is rotated into position, the index card that was passed out to my in-person students yesterday is going to be used as your measurement tool today. That means I am going to be using that index card to figure out how long this triangle is, this side of that triangle, so that when it is rotated, I can observe whether or not it is the same side length. Is it still just as long? So again, we're using that index card to say, let's see, here's the corner of that index card. It goes to this point in the index card. Is it the same in this original triangle? At this point, we can indeed come to the conclusion, and so we are writing it down that the side lengths stay the same. I know it might feel like that's something that is very obvious, but again, we're leading to a very important conclusion and new vocabulary term. I don't want to just measure those side lengths though. As the directions say, we also want to measure each angle, which means I'm going to be using tracing paper to measure those angles, and I'm going to trace out that angle here and see that angle is 30 degrees. So now that it's on my tracing paper, I can move that angle around, spin it around so that it lines up here and say, is it really the same over here? It is, which means that I can now label this the 30 degrees that it asked me to do in the directions, because I know for sure that it's 30 degrees. Similarly, I'll do the same with the 60-degree angle, trace it on the tracing paper, move it around, measure is that other angle 60 degrees, just like that one was. And it looks like it is also 60 degrees, so I can go ahead and write that down. This one I don't really even need to measure because I can see that it was the 30 plus the 60, so that one is obviously 90 degrees there. And our final transformation is a reflection. You're definitely going to want to make sure you're using your tracing paper. Online students, you're definitely going to want to be using your applet to do that reflection. Once that reflection is done, then you'll want to find out, are the lengths the same using our index card? Are the lengths the same? Using the tracing paper, are those angles the same? I'll be using my own version of technology. I won't be using the applet. I'll be using it up here so that I can perform my own reflection and come to those conclusions. So now I can flip this left to right, and in position it's going to be right here. And again, using that tracing paper, it's easy to conclude that this is indeed 150 degrees. This is 90 degrees. Just as this was a 90-degree angle, this was a 90-degree angle. And this was 120 degrees. So all of the angles ended up being the same, but even more than that too is these side lengths. Again, it's kind of hard to measure sometimes when it doesn't fall exactly on one of those crosshairs where all of the corners meet together. But I can see this is how long the line segment is here. And sure enough, that's how long it is in the reflection. So we can see that once again, the side lengths and the angles were the same. So I'm writing that conclusion down. The side lengths were the same measure. And the angles were the same measure. And that leads us to the big conclusion that I need you to come to, this new vocabulary word, rigid transformation. Now be careful when you hear this word. Some of you think that it has a certain meaning. This is rigid, R-I-G-I-D, which is different from ridged. Okay? These are different things. They might sound the same, but they are not. You guys might understand that this is an edge or something sharp or pointy, or even you can think of it like a really bumpy road. We're not talking about that. We're talking about this word rigid. And what rigid means is it means unmoving. It means firm. It means unchanging. It's set in its ways. So understanding the meaning of that word rigid, when I think of a rigid transformation, not transform, sorry, a rigid transformation, what that means is they are transformations that preserve, that means stay the same, angle measures, and side lengths. Pencils are moving because this is a very important conclusion to come to. This is the only place you'll see this vocabulary word. Not just side lengths, but I'm also going to say distances. So continuing on, this last activity says which one? We have triangle ABC and we have two other triangles. Triangle ABC can become one of the other triangles using a rigid transformation. Again, that would be a transformation that doesn't change the size of the angles or the size of the sides. It keeps the side lengths and it keeps the angles. Take just a quick second of think time. Which of those triangles, DEB or CFG, is the one that can be obtained from a rigid transformation? I think it's easy to see that that would be triangle CFG, because triangle EBD is too small. If it's too small, that means it did not preserve the length the way that it was supposed to. So what is that rigid transformation that can take triangle ABC to our new triangle CFG? That was a rotation 90 degrees clockwise about point B, I think. No, not B. B is the easiest one actually. And then once it rotates around point B, then we can just translate it 7 units to the right. This "Are you ready for more?" is a really great exercise. I will leave that to you to work on your own. Pause the video, give yourself a chance to work on it. Pause the video if you haven't done so already, because the answer is coming up. The perimeter of each L-shaped region is 25 units. Here is your lesson summary. We are going to highlight the key pieces that are the most important. The transformations we've learned about so far, translations, rotations, reflections, and even sequences of those motions are all examples of that new vocabulary word, rigid transformation. A rigid transformation is a move that doesn't change measurements on any figure. We can continue reading. Earlier we learned that a figure and its image have corresponding points. With a rigid transformation, figures like polygons all have corresponding sides and corresponding angles. We can see all of that listed here below in this table. Triangle ABC was first reflected and then translated to become triangle EFD. And AB is this side length that corresponds to EF. Notice they have the same measure. And I'm not going to read through that whole chart and that whole table. Notice measure ABC, this angle has 71.6 degree angle. And its corresponding angle, F, has the same measure, 71.6 degrees. Now it is time for your cool down. We have trapezoid A, B, C, D, and this is going to be trapezoid A prime, B prime, C prime, D prime. With that in mind, knowing that this was a rigid transformation that took A, B, C, D to A prime, B prime, C prime, D prime, you can figure out where each of those labels should be. For example, this was B, so this is going to be labeled B prime. This was C, so corresponding side angle will be C prime, D prime, and A prime. We can also see that C prime D prime has a length of 4, so that means CD would also have a length of 4 because we're not changing the measurements at all. And A prime D prime had a measurement of 6, so AD will also have a measurement of 6. And we can use that going the other direction too. Angle A and A prime would both have 130 degree measures, and B and B prime would also have the same measures, 50 degrees there. Your homework is Lesson 7 practice problems. For you online learners, this is one that I think you are also going to need to print out and then upload an image. You will have to print that out and upload an image. For you in-person students, obviously you'll just be doing it on that packet that I gave you. That's it. We'll see you next time.